Fluids in the body. Fluid systems in the body. By Assistant Professor of Medical Physics, Dr. Al-Arif. Blood flow in vessels. The flow of blood in arteries is affected by changes in the heartbeat rate and stroke volume, which is the volume of blood pumped per beat, and also by changes in the arteries themselves that control their diameters by chemical and neural mechanisms. The veins and arteries are not rigid pipes but are elastic and alter their shape in response to the forces applied by the fluid. The pumping action of the heart, that is, blood pressure, flow volume and rate of heartbeat, is regulated by a variety of hormones. Hormones are molecules, often proteins that are produced by organs and tissues in different parts of the body. Hormones affecting the heart are produced in response to stimuli such as need for more oxygen, changes in body temperature, and various types of emotional stress. The power produced by the heart, P-heart, is the product of the flow rate, Q, and the energy, E, per unit volume of the blood in unit of erg per second. At rest, when the blood flow rate is 5 liter per minute, or 83.4 cubic centimeter per second, the kinetic energy of the blood flowing through the aorta is 3.33 times 10 to the power of 3, erg per centimeter cubic. The energy corresponding to the systolic pressure of 120 torr is 160 times 10 to the power of 3, erg/cm cubic. The total energy is 1.63 times 10 to the power of 5, erg per centimeter cubic, the sum of the kinetic energy and the energy due to the fluid pressure. Therefore, the power, P, produced by the left ventricle of the heart is 1.35 times 10 to the power of 7. As the blood flows through the circulatory system, its initial energy, provided by the pumping action of the heart, is dissipated by two loss mechanisms. L. Os is associated with the expansion and contraction of the arterial walls and viscous friction associated with the blood flow. Blood vessels have elastic walls which have tendency to contract. Vessels may collapse and burst due to wall tension comes from rapid increase in the pressure pulse travels along blood vessel. The pressure causes tangential tension, Th, which is proportional to the inner radius, Re, and the wall thickness, H, according to Laplace law which stated that the tangential tension is equal to the pressure times the inner radius divided by the wall thickness. It is clear from the equation that the tension is proportional with pressure and inner radius, but inversely proportional with thickness of the wall. The below table shows the pressure conditions in various blood vessels of the cardiovascular system. Larger radii are correlated with thickness of the walls to balance the tensions. The flow rate, delta V over delta T, of blood through a vessel is directly proportional to the pressure difference between any 2 points in the vessel, delta P. And the fourth power of the diameter, D, and inversely proportional to the length of the vessel, L. And fluid coefficient of viscosity, eta, according to Poisson's law as in the equation. Diffusive gas exchange in the alveoli. Another area in which fluid as a gas interacts with the body is in the respiratory system. The main purpose of the respiratory system is to transport oxygen from the outer environment into the bloodstream and supply the body with the necessary fuel for the oxidation processes. Second purpose is to remove the rest product of the oxidation process CO2 from the blood and exhale it to the outer environment. The inhaled air is a gas mixture of about 80% N2 and 20% O2. The exhaled air is 80% N2, 16% O2 and 4% CO2. The average rate of breathing is about 61 per minute, which is equivalent to 1.6 times 10 to the power of 23 of air molecules per minute. The gas exchange takes place by diffusion through the surface membrane of the alveoli system. The alveoli are small gas bubbles with radius of about 0.2 mm, at the end of the bronchial system. The lung system has about 30 million to 300 million alveoli, see the figure. The alveoli have a liquid layer between the wall and the air volume. The tension pressure, P, inside the alveoli is directly proportional with surface tension of the liquid, gamma, and inversely proportional with the alveoli radius, R, according to pressure equal to 4 times the surface tension divided by the radius of the alveoli. The liquid surface tension varies with radius, which tends to keep the tension pressure inside the alveoli constant. The alveoli are surrounded by capillary blood vessel system. The surface area, A, of the entire alveoli system is about 80 square meters. This allows perfect and efficient gas exchange mechanism in the alveoli. The purpose of the diffusion process is the exchange of O2 with CO2. The diffusion flow depends on the size of the molecules, sigma, and the number of particles per unit volume, n. This determines the mean free path, lambda, of a molecule without interacting with other molecules. The mean free path is given by lambda equal 1 over n times sigma. The average distance, d, a molecule can travel after n collisions are given by d equal lambda times the root of n. Since the time for the molecule to diffuse is proportional with the number of collisions, therefore d proportional to lambda times root of t, the diffusion constant, k, of the molecule in the medium is equal to k times d divided by 6 pi times the radius of the molecules times the coefficient of viscosity, where k times d is the thermal energy of the molecules. This information allows determining the time necessary for oxygen molecule to diffuse through the entire alveoli bubble and through the alveoli membrane into the capillary vessels. Given 3 problems to be solved by you. Please check your result with the given answers.